Hi, this is Javier Encinas, and today we're going to design completely from scratch a cantilever retaining wall supported on piles using ASDIP RETAIN. This is a real-life example. It's a structure that I designed recently. It's part of a parking garage building, precast building. So this cast-in-place retaining wall is part of the access ramp of the building. The stem height is 11 feet. The backfill is 120 PCF density, and it's a wood quality material with internal friction angle of 30 degrees. It will be subject to traffic, so this surcharge of 250 PSF will model the traffic. The building above is precast, but this portion of the building reaction is dead 13 kip per foot and live 5.4 kip per foot. This is directly on top of the stem of the wall. Due to the poor soil conditions, the soils report has recommended these allowable pile loads. Axial compression 180 kips. Axial tension 50 kips, and the lateral load per vertical pile 10 kips at the top. So using this information, we're gonna model this in ASDIP RETAIN. Let's open ASDIP RETAIN. Let's create a calculation. Let's say a ramp, any name. So the calculation is added to the tree, double click on the tree. And this is the retaining wall form. In the geometry, we're going to define the stem height, which we know that is 11 foot. And let's use a stem of 12 inches at the top and also 12 inches at the bottom as a first trial. So we are modeling this portion of the wall. Let's input the loads first, and then later let's continue with the footing. Let's move to the loads. Okay, the backfill density is 120. It's exactly what we have. Internal friction angle, we said that is 30. We don't have a water table, so 0 here. Surcharge, the surcharge, we know that we need to model 250 PSF. Let's do that. 250 PSF. Concentrated loads, we have also concentrated loads in our example. 13 and 5.4. Let's input that. 13 as dead, 5.4 as live. No wind, no seismic, so we are done with the loads. Let's go back to the geometry and let's focus on the footing. Since we are using piles, the soils report has recommended steel piles, HP 12. So the minimum spacing is 3 times the pile diameter or the pile size. In this case is 1 foot, so the minimum spacing between piles would be 3 feet. Let's use that 3 feet between piles plus the edge distance. So it's 3 plus 1.5 and 1.5 is 6 feet footing length. So let's go to the footing tab. The program is assuming that we are not using piles. We are, the wall is supported directly in the soil. This is not the case. We're using piles. So let's click here. Footing thickness, let's say 36 inches for now. The toe length, this portion. We know that the total footing length is going to be 6 feet. So let's say 2 feet. Plus 3 here is 5, plus the stem thickness, which is 1 more foot, is 6 feet. So it looks like that. So our wall will look like that. In materials, piles, this is the capacity of the piles. Let's go back to the example. It's 180 in compression, 50 in tension, and 10 in lateral. Let's input that. 180 here, 50 in tension, and 10 in lateral. Okay, now we have defined the geometry and we have defined the piles capacity and the footing. So let's see the numbers. In actual, obviously, we are, it's only 35% of the actual capacity and 9%. So we are, very comfortable with that. We can increase the spacing if we want. In the horizontal portion, we are not so good. It's over. The capacity is 5 kg per foot, and we are applying 5.4, so 5.5. So we need to increase either more piles for capacity, for a lateral capacity, or we can batter, this pile. That's probably the best solution. Let's increase first the actual the spacing to reduce the actual ratio here. Right now, at the toe, the piles are every 3 feet. Let me show you in plan view. Looks like that every 3 feet, which is very close spaced. We need to increase that probably to 5. Let's see the numbers again. 58%, 104 versus 180. We can increase it even more. 6. Okay, we are now 70% of the capacity. It's probably okay. Remember that is still vertical. We haven't battered it yet. It's vertical. At the heel, it's also very lightly loaded, 16. So we can increase it even more in the heel. So let's see it in plan. At the heel, we probably every 10 feet. Let's see the numbers. 16%, so we can increase it even more. Maybe 12. 19%. It's very lightly loaded. So the pile at the toe is controlling the design, is more heavily loaded than the other one. But the horizontal capacity is what we need to pay attention to. So let's batter this pile. See the toe pile. Batter here. Let's say 14 degrees, which is about 1 in 4. Okay, now it's better. Let's see how the numbers changed. So now the horizontal capacity is okay because with the battered piles it's taking all the lateral load in actual. So we are with this configuration we are 72% for the pile at the toe, and the actual and the horizontal capacity is okay as well. Here the program is showing a failure in shear, in footing shear. Let's go to the footing tab here. This is the shear diagram and the moment diagram of the pile cap for this load. The footing is already 3 feet deep. We can increase it a little bit more, the thickness if we want, but in this case, if we use the strut and tie theory, it's obvious that this load, this vertical resultant, will be distributed to the piles, similar to a truss. So probably the shear capacity is going to be okay in this situation. This is the moment diagram, so we can size the rebars accordingly. So we can see more detailed information on the condensed tab. You see in the stem design, this is the variation of the moment along the stem. We can see it also graphically here. This is the variation of the moment. So we are providing this blue capacity according to these rebars at the stem. This break here corresponds to the cutoff rebars at 7 foot. We can probably lower it down a little bit. 6. So this moves down a little bit, is more optimized. The shear at the stem is perfect. So let's go to the footing. We discussed already the one-way shear. The minimum steel area obviously is failing because the pile cap is very thick. So let's use, say, number 7. Number 7. Still over. So number 8. Yes, that's what it is. So now the minimum steel area is satisfied, 86% using number 7s. In the detail tab, you can see all the calculations with exposed formulas and a reference to the code. You can check every single calculation, so all the forces and pressures on the stem. Graphically, you can see the pressures there. These are the pressures. These are the actual forces on the piles. We can clearly see that they are under the actual capacity, 72%. So the pile capacity ratios are okay. The stem, we discussed already the moment and shear diagrams with the corresponding rebars for the controlling load combination as well. The footing, already discussed the shear and moment diagram at the pile cap with this pile configuration. And finally, in the construction tab, you can see the reinforcement that you just designed in section and in elevation. We complete the design in a few minutes, and thank you for your attention, and we'll see you in the next video.